on in, everyone. Feel free to ask me any questions before we get started. Infinity, did you get my email? I finally replied to you. I just want to make sure you got it.
Let me check right now.
Okay. Anybody else has any questions? Like I said, it's actually time to start class, but I can wait a couple minutes in case anybody has any. Those of you that have lab tonight, you actually have your test this evening. Miss
Lab is
Ray.
tomorrow.
Oh, is lab tomorrow? Okay, that's cool. It makes better sense.
Yeah, that was actually my question was, is the test due tonight or
No, it's
tomorrow?
face-to-face tests will be done during your lab time. For some reason, I was thinking it was tonight though instead of tomorrow. I'm just used to the tests aligning on the same day of the week as the actual class.
Yeah, I got the email.
Gotcha. Okay, thanks.
Okay.
All right. Well, we got 8 of you in here. I guess it's best to go ahead and start on. So one thing I wanted to let you know is probably there's one diagram in your book that's more important than any other diagram, especially in this first semester, if not in the entire 2 or 3 semester sequence if you take it. So I'm going to open up to that particular diagram and then share my page with you. Let's hold on a second. Excuse me while I just die. Clearly, I'm pretty sure I got tuberculosis now. Good old Doc Holiday and me. I'm your Huckleberry. I crack me up. I'm one of the funniest people I know. All right, so I'm going to pull this up to chapter 3. And specifically, I'm going to go to chapter 3 regarding projectile motion. There's the diagram I want. Okay, so let me stop a second and share the screen with you guys because this, like I said, is the single most important diagram in your book. So what I want you to understand about this diagram is this is basically taking a series of photos, or you can think of it as sort of leaving the aperture of the camera open and then having a flash going bam, 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 like every 10th of a second. And each 10th of a second, it obviously exposes the film or the electronic detector in such a way that you get a shot. You can't really see the red ball right here that corresponds to this yellow ball, but the deal is this red ball and this yellow ball are sitting in a holder that synchronizes their release. In the case of the red ball, it's released to drop straight down with no initial velocity. In the case of the yellow ball, it's released and shot horizontally. Horizontally for some velocity with some velocity. No component in the y direction, and that's important. So it's not speeding up or slowing. Well, it's not moving at any velocity vertically. But what you see is if you go down to the third time frame, that's this ball and this ball, and then the fourth is this ball and this ball, and then you can really see it by the fifth, which is this ball and this ball. What that shows you is that the horizontal motion and the vertical motion are completely independent of each other. It's kind of weird, but imagine if we were in an area where the air resistance was negligible and we were out in Indiana or somewhere else that's equally exciting on the horizon. In other words, a flat plane. And I took a rifle and I shot it perfectly horizontally. So I put a level on it and I, locked it down to make sure it wasn't shooting downward by any angle or upward by any angle whatsoever. And I fired the rifle, and then I had a little light detector at the end of the rifle that the instant the bullet blocked that, it would drop something about the same size as a bullet from the same height as the barrel, and therefore the bullet. And oddly enough, what this picture shows is that that projectile, that bullet leaving that rifle, will travel a long distance horizontally, but will in fact hit the ground at the exact same time as the one that was just dropped vertically. Okay. That's sort of, like I said, your conclusive proof that the vertical motion is entirely independent of the horizontal motion. So for that reason, when you go to solve a projectile motion problem, you're sort of going to break it up into two problems. The first thing you're going to do is break up the initial velocity into an x component and a y component. And then what you're going to then do is take the vertical component and you're going to treat that as a ball thrown straight up. And you can use that, for instance, you can make an equation for y as a function of time using x equals 1/2 at squared plus v0t plus x0. And that equation, in some sense, lets you figure out how long the projectile will be in the air. Now you'll have also an equation for the horizontal motion, and you can actually use x equals 1/2 at squared plus v0t plus x0 again. Only since we're ignoring air resistance, you will have no acceleration in the x direction. So the 1/2 at squared term will disappear. You'll just have x as a function of time is equal to v0x times t plus x0. Okay. Now, if you take the time at which the projectile was able to fly all the way up and then come back and hit the ground, if you plug that into the x as a function of time, it will give you how far the projectile was away from you when it hit the ground, and therefore you can determine how far the projectile went. That's the whole point. Okay. Not only that, you can take that y as a function of t, you can take the derivative, and that'll give you the velocity in the y direction as a function of time. And you can take the derivative again, and that'd give you the acceleration in the y direction as a function of time. You can do the same thing with that x equation, which of course doesn't have the 1/2 at squared, but you can take the derivative of it, and that'll give you the x component of velocity as a function of time, which is just going to be a constant because there's no air resistance. And then the acceleration is just going to be 0. Okay. So hopefully that will help you make some sense of how to solve a projectile motion problem. Now I'm going to stop sharing that screen, and I am going to go and solve a generic projectile motion problem. So this is going to be a projectile motion problem where I'm using symbols as opposed to actual numbers. And the symbols represent numbers, and I'm going to tell you which ones you can pretend you know. And I am going to treat it generically that way because when you solve a problem symbolically like that, you solve an infinity of problems. For every different initial value that you're given is another problem that you can solve. I'm going to solve it that way. And I'm also going to assume that the projectile left from the same height that it lands at. And that makes it a little less general, mainly because you can get some very general results that you can use over and over again, but they're not going to be equations that are allowed on your equation sheet. But if you take the time to memorize them, then they would be very helpful to you. Then the next problem I'm going to solve is one that is actually very specific with numbers, and that will make it a little bit easier because I'm going to, in that case, examine a case where the ball is launched at a different height than it lands. So let's go ahead and start off doing that. I'm going to actually share my screen because I often forget to do that. I'm going to go ahead and share my screen from the iPad. And it looks like it's not making me download something that I've downloaded 1,000 times. So yay. Now we're just waiting for the process. Okay, I'm going to go ahead and draw a coordinate system, which will pop up for you in a second. Ah, there it is. Okay. So what I'm going to say is that's my coordinate system. And this is going to be y. and that's going to be x. And what I'm going to imagine is that I have some sort of cannon device or whatever that basically the projectile will be fired, and the instant it leaves the barrel of the cannon, it will be at the origin. So that means my initial position, x0 and y0, will both be 0. That makes it kind of nice. Not only that, it's going to have a velocity whose magnitude is v0 and whose angle is theta. So we're pretending that we actually know the v0 and the theta. This right here would be called the initial velocity vector, but me writing the v0 without the vector symbol just tells you that, hey, that's the magnitude and that's the direction. Now, you probably know the name of the path it's going to trace. Anybody know the name of that shape right there?
Parabola?
Yes, it's a parabola, and I could actually show you how to confirm that y versus x is a parabola, if you want to. What you're used to seeing normally is y of t, and that gives you a parabola. X of t doesn't, but y of x gives you a parabola as well, and that's what we're looking at. Now, what I'm going to call the distance away that it lands, I'm going to call that r for range. And that's one of the things that I want to find. I'm also going to say that happens at a time t sub ht, which is what we call hang time. In other words, how long is it in the air? So it's the same parameter, for instance, that we use for punters in the NFL. You want to really know how long the ball can be in the air so that your either your blockers can get downfield and help the runner, or your tackles and people that want to make the tackle can get down there. So you want that time to be as large as possible. So that's going to be called hang time. And I also want to know the final velocity there as well. So that's 3 parameters I want to know. I also want to know right here, there is a height, which I'm going to call h max. And I would like to know what that is as well. And that sort of covers all of the things that you're typically asked to do on projectile motion. Notice that by having the x-axis horizontal and having it leave at the origin and land on the x-axis tells us that it left and landed at the exact same height. So that's what I'm shooting for here. So, and the only variables I assume I know is v0 and theta. So assume we know v0 and theta. So all of our answers has to be in terms of those variables. We also know a, the acceleration, is equal to negative g, and I'll put a j hat on that. Notice I said negative g. That's because the acceleration is positive in the downward direction, so it actually goes downward. That means since I chose upward as the positive y direction, then the acceleration has to be negative. So that's why I have a negative g, and that's of course 9.80 meters per second every second. So we can also assume we know g. So g is allowed to be in there, as is v0, as is theta. So what I'm first going to do is use my kinematic equation to find y as a function of t. We're assuming no air resistance. And that implies A is only due to G. In other words, there's no acceleration in the horizontal direction, and the only acceleration that happens in the vertical direction is the acceleration due to gravity, which means it's going to, as it's going up, every 1/10 of a second, it's going to slow down by 0.98 meters per second. And every whole second, it's going to slow down by 9.80 meters per second. Okay. Now, once it gets to the peak, and then starts heading back down, then it's speeding up by 9.8 meters per second every second on the downward direction, but the acceleration stays the same all the way through. So I'm going to use my kinematic equations. I'm going to rewrite it though in terms of y instead of x because I have an acceleration in the y direction. So I'm going to say y of t, that's the height as a function of time. That's going to be equal to -1/2 gt squared. Now, something you might not see, so I already automatically. So before I finish this completely, what I want to do is I would like to draw this vector v0 in terms of its components right there. This one is v0y and this one is v0x. And I think you can see that sine of theta, which is or some old horse, is opposite over hypotenuse. So that's v0y over v0. And then cosine theta is ka or K-Mahapan or adjacent over hypotenuse. So in this case, it's v0x over v0. So I now know how to solve that. That's what I was talking about last time when we did the addition of velocities. I mean, addition of vectors is it's perfectly fine to go ahead and write out what sine and theta are, and until you get more comfortable with doing this kind of stuff. So what I did was just took that time there to show you exactly what I meant by that. So I've broken down the vector, the initial velocity, into x and y components so that I can now write down y of t. Now remember, the equation is x equals 1/2 at squared plus v0t plus x0. So I need the initial velocity. Since this is the y of t, I need the initial velocity in the y direction. So I'm going to write, I'm going to write it in blue. So I'm going to write plus, because notice the initial velocity is upward. So that's the positive y direction. And the answer is going to be v0 sine theta. So I'm going to put v0 and then I'm going to put t and then I'm going to put sine theta, because if I put the t after the sine theta, it might be a little bit ambiguous as to whether you think you're taking the sine of theta or the sine of theta times t. And then the initial position is just 0, because we said it's at the origin. Okay. Now I'm going to use the exact same equation for x as a function of t. Only in this case, the acceleration is 0. So I get v0t cosine theta plus 0, because lo and behold, x0 is equal to 0. Okay. So those are my two equations. And in fact, if you really like vectors, you can make up a vector field, if you will. And the way you do that is you could say r vector as a function of time. That's usually what they use, the letter r instead of x or y or z, because x and y and z are normally associated with the x direction, y direction, z direction, and r can sort of be considered any direction. So what we could do is we could say r of t is equal to v0t cosine theta I hat, and then minus, actually I should probably say plus. Yeah, I'll do plus. Plus, I'll put parentheses, minus 1/2 gt squared plus v0t sine theta, and all that multiplied by j hat. So that's actually your velocity. I mean, that's your actual position vector. Notice if you just figure out what v0t cosine theta is, multiply that by I hat, then that's going to tell you how far to the right of the origin the particle is at that particular time. And similarly, if you do the same thing with the part in front of j, that's going to tell you how high up it is. And you can, of course, say v of t is just dr over dt, which gets you, of course, if I take the derivative of v0 t cosine theta with respect to time, I just get v0 cosine theta I hat plus, now if I take the derivative of this stuff with respect to t, the t squared becomes 2 times negative 1/2 gt. So that's going to be negative gt plus v0 sine theta j hat. And then, of course, you could also go a little further and say, well, a as a function of time is another vector function that's dv over dt. And if I take the derivative of that, I just get negative g j hat. So that's just some extra stuff I did just to show you. Very few people ever use this approach to solve projectile motion, but it can be done. And I'm also using it to remind you that, hey, if I need to know the velocity as a function of time, all I really got to do is take the derivative of that y of t to get the y component of velocity as a function of time. And if I wanted it for x, I just take that x of t and take the derivative. Okay? So let's start off with A. I want to know H max. So H max equals basically y of t when v sub y of t is equal to 0. In other words, when you throw a ball up, it reaches its max height when the y component of velocity is 0. Right? So what I want to do is figure out at what time the y component of velocity is 0, and then plug that time into y of t, and that'll give me H max. So v sub y of t is equal to d by dt of, now I'm going to take, oops, I didn't write that very clearly. That's d by dt of, now I take y of t, which is negative 1/2 gt squared plus v0 t sine theta, like that. And that, of course, gives me negative gt plus v0 sine theta. Remember, all we're supposed to know is theta, v0, and g. So if I solve this for vy of t equals 0, then what I get is 0 is equal to negative gt plus v0 sine theta, which implies t is equal to v0 sine theta over g. So that means this time right here is equal to v0 sine theta over g, and that's all from that one process that I went through. Now all I got to do is plug that into y of t. That's going to be negative 1/2 gt squared. Now the t squared becomes v0 sine theta over g, and now I got to square that. Plus I have v0 times v0 sine theta over g times sine theta. In other words, that's me replacing the t between the v0 and the sine theta with that time. All this is supposed to be H max. Okay, where t is specifically that guy, which of course is that guy, which of course is that guy. So now I can say H max, doing a little simplification. Notice I'm going to square v0 and sine theta over g. the g in the bottom becomes g squared, canceling with one of the g's in the top. So this is going to give me negative v0 squared sine squared theta over 2g. And then the other term, which is going to be positive, becomes v0 squared sine squared theta. Now this one's over g alone. So what I'm going to do is get a common denominator by multiplying by 2 over 2. And that gives me that h max is equal to, now you can see it's 2v0 squared sine squared theta minus v0 squared sine squared theta. So that just gives me v0 squared sine squared theta over 2g. And that's the answer for h max. So again, this is not an equation I would normally allow students to have on their equation sheet, but if you memorize it, it can come in handy. Okay. But we're not wanting you to just use that kind of equation. We actually want you to go through this process. So you might not get this right now with these symbols, but you can go back and say, hey, let's do exactly what Mr. Younger did in this example, only I'm going to call V0 40 meters per second, and I'm going to call theta 30 degrees. And then you work it all out, and one by one get all these answers, doing the exact same things I did. And what you'll find is you'll get the same answers if you plug it into this equation. Okay.
Those little equation sheets you had at the bottom of the tests. Do we need to print those out and bring them to the lab tomorrow, or are they going to be provided for us?
No, they're going to be in your tests. And
Oh, okay.
Tests. Yep.
Oh, okay. It's going to be on Canvas then?
Yep.
Okay.
Yep. That allows you to get your grade immediately and sort of nice little stuff like that. So, all right. So you've got H max now. That was one of the things we did. And we also were able to find the time, which I'd normally call that like T1/2, which is, you can probably look at the symmetry of it. It should be about half the hang time, because the hang time is the total time it's in the air. It takes half that time to get to the peak, and then it takes half that time again to get from the peak to the bottom. So you could also subscript this with red, say 1/2, and then you could box that off if you wanted to. By symmetry, you expect the hang time to be twice as long. And we're going to see that pretty soon. So let's go ahead and attack part B. And I didn't necessarily call any of these part A or B or whatever. I'm just doing it now. So let's look at part B, which is where I'm going to find the hang time. So T hang time is equal to question mark. But what I do know is that Y of T hang time is equal to 0. Does that make sense? Everybody see why that is the important equation for me to use? Because T hang time is the time required for it to go all the way to the top of its motion and then hit the ground again. So its height is going to be 0. Of course, there's more than one time at which it's 0. And lo and behold, you're going to discover that that actually pans out as well. So now what I'm going to do, assuming everybody knows that, feel free to ask me questions. I'm trying to ask you in case you have problems, but feel free to ask me too. So now what I'm going to do is take that Y of T up top and set that equal to 0. So I'm going to say 0 is equal to negative 1/2 G T squared plus V0T sine theta. Now, hopefully y'all remember your rules of factoring. And the first rule of factoring is whenever you go to factor something, the first thing you want to do is get rid of any greatest common factors so you can make the actual factoring process easier. So that's what I'm going to do here. There's a common factor of T. So what I'm going to do is say 0 is equal to T times, now I get negative 1/2 GT plus V0 sine theta like that. Now, what this is telling us is I have two numbers, t, and that stuff in parentheses, multiplied by each other, and the answer is 0. The only way that's possible is either t is 0, which is exactly what happens initially. So that's what that particular solution is for, is when it was initially taking off out of the cannon. But the other option is 0 is equal to, in this case, it's going to be -1/2 GT plus V0 sine theta. So that means T hang time is just equal to 2 V0 sine theta over G, which notice that's exactly twice as long as T1/2. So like I said, I expected it to be about twice as long as T1/2. So that's a nice check for us as well. So now I have the hang time. That's 2 V0 sine theta over G. Any questions on that one? All right. So I'm going to go to part C, which is I want to know the range. Now, what I do know is that the range is equal to x of t hang time. In other words, if I plug in the hang time, the time that it takes for it to actually hit the ground again, if I plug that into x of t, that'll give me exactly how far to the right it's went in that time. So I'm just going to do that now and say, lo and behold, I have V0 times 2 V0 sine theta over G, make sure that theta is there, and all that times the sine of theta that was already there. So what I get is, of course, this is 2 V0 squared. Oops, sorry, I made a copying error there. That's not sine theta that's out here to the side, that's cosine theta. Okay, because remember the x of t has V0 t cosine theta. So this is going to be V0 squared sine theta cosine theta, all that divided by G. Well, it turns out that 2 sine theta cosine theta is in fact equal to the sine of 2 theta. So I'm now going to say R is equal to V0 squared sine of 2 theta over G. And that's our range equation. That 2 theta also gives us the idea that there are two trajectories. Because notice your theta can run from any angle up to 90 degrees. And if you look at it that way and you think about the graph of the sine of 2 theta, let me write that over here. This is theta. And this is going to be the sine of 2 theta. What you get is a graph that looks like this, where this part would normally be 2 pi, but because the argument is 2 theta, it's actually just going to be pi. And then this is going to be pi over 2. And this is going to be pi over 4, which is 45 degrees. So for any but the angle that results in sine of 2 theta equal 1, you're actually going to have two different angles that give you the same distance. This one's the high trajectory, and this one's the low trajectory. So if you ever seen poor Shaquille O'Neal shoot a free throw, you'll notice that he actually uses the low trajectory, and that's why he's kind of a crappy free throw shooter. But if you look at Michael Jordan or LeBron James or some of the more gifted players that actually have decent free throw percentages, you'll see that they generally use a little bit higher trajectory. And the way it works is basically if you find an angle that gives you the right distance, if it's bigger than 45, subtract 45 from it. Let's say it was 65. If you subtract 45 from 65, you get 20. So that means if you subtract 20 from 45, you'll get the same distance. So 25 degrees gives you the same as 65 degrees. They both give the same range. Does that make sense to everyone? So I've basically solved for everything but the final velocity now. Okay, I'm going to flip to the next page and say that was part C. So I'm going to say part D now. So I want V final vector equals question mark. Well, since we're not dealing with air resistance, we know that V final sub x is just V0 sub x, which is V0 cosine theta. So I don't have to mess with that at all. But I also know that V final y is just V at t halftime, or excuse me, hang time. Does that make sense to everyone? So V final y is equal to V of t hang time, which is d by dt of y of t, and then you evaluate that at t halftime. Remember, if you put in the t halftime or hang time and then take the derivative, you just get 0 because everything's a constant. So you actually have to take the derivative of t of it with the t in there and then substitute the right number. Well, we know that the derivative of y of t is negative gt plus v0 sine theta, like that. So now we're going to plug that in, that t hang time in. And for that, I get V final y is equal to negative g times 2v0 sine theta over g. Double checking that's my hang time. 2v0 sine theta over g. Yes, it is. Plus v0 sine theta. You see, in this case, the g's do cancel out, and we get 2v0 sine theta with a negative sign plus v0 sine theta, which gives us basically just negative v0 sine theta. Now notice that is just the negative of v0y. So from that alone, you can tell what the angle is going to be and all that good stuff. But I'm going to go ahead and show you all the gory details so you better understand it. What we have now is we have a vector and we have two components. And just like the end of adding vectors, when you have the two components at the end, you need to combine them to make the new magnitude, and you need to do some stuff to find out the new direction. So what I'm going to do is I'm going to draw a coordinate system like so. There's my x-axis, there's my y-axis, and what I have is this part right here is just V0 cosine theta. And then this part right here is negative V0 sine theta. And this part is V final. This angle right here, I'll call phi. Okay. So I see that I have V0 cosine theta. Those are numbers we know. And I have negative V0 sine theta. Those are things that I know as well. So I can use the Pythagorean theorem and say that V final is equal to the positive square root of V0 cosine theta quantity squared plus negative V0 sine theta quantity squared, which is going to give us the positive square root of V0 squared. Notice the V0 squared is going to appear in both terms. So I'm going to take this opportunity to factor it out. And then all I have left is cosine squared theta plus sine squared theta, like that. Anybody know a trig identity about sine squared plus cosine squared?
It equals 1.
Exactly. So that's just 1. And then, of course, you end up getting, oops, wrong color. You end up getting just V0. Okay, so the magnitude actually has the same magnitude as the original one, which we sort of knew because, like I said, everything looked the same. The only thing that changed was the direction of the y component change. Now, the other thing is we need to know phi, and through our alley, our TOA means tangent equals opposite of or adjacent. So the tangent of phi is equal to the opposite. Notice how I do not put any signs in. It's just V0 sine theta and then V0 cosine theta. I don't put signs in. Okay. We can see that the V0 is going to cancel out. And what you ultimately get is phi is equal to the tangent inverse of, anybody know identity regarding sine over cosine?
It equals tangent? No, wait.
Exactly. Yep, that's right.
Okay. Yep. Okay.
So it's the inverse tangent of the tangent of theta, which means phi is just equal to theta. So we can say that V final is equal to V0 at negative theta. And that's it. Any questions on that? All right, so let's recap exactly what we did just so we can make a little bit more sense of it. So one thing I'll tell you is I've learned over the years that if you're thinking about this being too much stuff to remember, then you're doing the physics wrong. That's not the way you want to do physics. You don't want to have a bunch of stuff to memorize. Okay. And I've heard this from other people like Richard Feynman, where the best way to think of these things is have some sort of physical model in your brain of what's going on. And everywhere that model fits the reality of how you solve it, you say, yay, that's good. But then you, of course, internalize the cases where it doesn't, and you'll end up having basically a good idea of exactly what the results are because of your story that you have, that physical model. Also, if you've ever read any of the books by Terry Pratchett, like The Science of Discworld and stuff like that, you'll notice he talks about the Science of Discworld is basically like a Harry Potter type college for wizards, and they're living on a flat world called Discworld, But like Harry Potter, they're all magic and stuff. But one of the things they call magical is narrativium, which is like a narrative. And that's important too, because as I was saying, if you make a story, then it's not about memorizing, it's just about understanding the story and the story making sense because of that physical principle you laid down. So all of that comes together to work with this. So I want you to think about physics not in terms of things that you're not familiar with, but in terms of things that you are familiar with. So let's start back from the beginning. If you're asked to solve a projectile motion problem, there's a lot of different things they can ask you for. Like they could give you the range and the angle and ask you what the initial velocity was. Or they could give you the time that it's in the air, that what we called hang time, and the initial velocity magnitude, but not the direction. And you could solve for the direction. There's all sorts of stuff that you're doing. But the main thing I want you to understand is no matter what, you've got to hypothesize the existence of an initial velocity vector. That initial velocity vector will have a magnitude v0 and add a direction of theta. And then you've got to break that down into components, a vertical component and a horizontal component. So that's what I did there, where I wrote sine theta equals v0y over v0, and I wrote cosine theta equals v0x over v0. When I do that, I can then figure out what the components of velocity are in the x direction and y direction by just solving for v0x and v0y, right? In this particular problem, I asked you the whole litany of things like what's the max height it reaches. So in part A, I start to say, okay, well, I know something about the max height. Specifically, I know that the max height is reached when the vertical component of velocity is 0. And that should make some sense. If the vertical velocity was positive, meaning it's, pointing upward, then it still had some oomph to go a little higher, so you weren't at the max height. Similarly, if the vertical velocity was downward or negative, then it came from somewhere higher where its velocity was 0, so you're not at the H max again. So that leaves you with the strict narrative that the height, the max height that you reach, occurs when the vertical component of velocity is 0. Now, another way you can think about that is, look how we got from y of t equals negative 1/2 gt squared plus v0t sine theta. How did we end up getting from there to negative gt plus v0 sine theta? We took a derivative, right? And then if you look right there, notice the little arrow, the little red arrow I have, it comes from a T, and then it's got like 3 little off arrows. But right above that little horizontal red line, do you see I've got 0 equals negative GT plus V0 sine theta? So that was literally the derivative of the y of t. And I set the derivative equal to 0. Do y'all know of any time in calculus where you'd set the derivative of something equal to 0? In Calc 1, why would you set the derivative of something equal to 0? Yes, Julio said max and min. That's exactly right. For finding what your textbook would have called extrema. Okay, that could be a maxima, that could be a minima, or it could be an inflection point. Notice that if you make a plot of y versus t, the max height occurs literally at an extrema. So you're literally taking the derivative of y with respect to t and set it equal to 0 to find the maximum. So that's a whole nother reason you can do it. And therefore you've got another story, another narrative to tell yourself that hopefully should keep you straight when you're trying to solve these problems. So that's what I did. I took the derivative of y of t to get the velocity in the y direction as a function of time. I set that equal to 0 and I solved for t. And from that, I got t is equal to v0 sine theta over g, which is what I called t1/2. I was not asked that, and I didn't ask you guys to solve for that, but it turns out if I plug that time in to y of t, then that'll give me the height at that time, which has to be h max. And that's what I did there with the little arrows pointing down, is I said h max is equal to y of t1/2. And that gave me v0 squared sine squared theta over 2g. So that's our max height. Everybody get that? Now the next part, I wanted to actually find the hang time. Now the hang time to me is basically the time that it's in the air, and I knew that it starts the instant it leaves the cannon and therefore is at a height of 0, and then it ends the next time the height is 0. So all I had to do is think, I want to set y of t equal to 0 and solve for t. So I did that. I set y equal to 0, and I set that equal to -1/2 gt squared plus v0t sine theta. And I used factoring, and I found out the only way that that could be true is if t equals 0, or if -1/2 gt plus v0 sine theta equals 0. And that gave me, in fact, t hang time is 2v0 sine theta over g, which notice is exactly twice as big as t1/2. Everybody follow that part? So I'm now down to that little red check mark. Now, when I wanted to find the range, I said, well, the range is how far that moving horizontal shadow can travel in t hang time. So all I needed to do was plug in t hang time into x of t, which you see is right below the diagram at the very top. So you see x of t is equal to v0t cosine theta. All I've got to do is put t hang time in there. So when I put t hang time in there, I did get r is equal to v0 squared sine 2 theta after using a trig identity. And that's where I got that formula. Does that make sense to everyone? Okay. Now the last part was finding the velocity, and I made use of the hang time again because the x component of velocity is not going to change at all. We ignored air resistance, so it's going to constantly be v0 cosine theta. The y component is going to get smaller, 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 come to 0, and then become negative and get larger, 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 but more negative, of course, until it just about reaches the ground, and that's the maximum velocity it'll get before. That's the maximum velocity it'll get, basically. So what I had to do is say, okay, well, what is that velocity when t hang time occurs? Because that's when it gets back to that initial height of 0. So I plugged that in, and lo and behold, I got just negative v0 sine theta, which is just a negative sign difference from the initial y component of velocity. In general, when you have two components of velocities, you then draw them in the x and y axes in a way that you can make sense of it. So you try to draw them to scale to some extent. Like if one is obviously 3 times larger than the other, then you want to make that sort of true, and you put the x one parallel to the x-axis and the y one parallel to the y-axis. You make sure it points in the positive direction if it's positive, or the negative direction if it's negative. And you use Pythagorean theorem to find the magnitude, and you use the inverse tangent to find the angle, and that's what we did. So any questions on that?
Does there happen to be like example problems of this on your YouTube?
Yes, there's more of them on there. So you can just look for projectile, do a search for projectile. And I'm getting ready to do another one that's a little more concrete. So this one, what I'm recommending you guys doing is assign those numbers. So take V0 equals 40 meters per second if you want, and then take theta equals 10 degrees or 20 degrees or 30 degrees, doesn't matter, and try to solve this on your own. using the same steps I do, but actually using numbers. And I think you'll find it's not that hard. That being said, let me go ahead and show you the next example. Okay. So this one's going to be a little more souped up. This one, I'm actually going to have the projectile leave a very different height from where it lands. I'm going to do some crazy stuff on this. So first thing I'm going to do is draw my coordinates. Oh, actually, I'll draw a diagram first. So let's say this is a cliff. And this is the ground at the bottom of the cliff. And I'm going to choose a coordinate system. You might not have chosen this coordinate system, but I'm choosing it and we'll work out how it works out. So this right here is going to be my x-axis. And that right there is going to be my y-axis. And I am going to say that this height right here is 80.0 meters. Okay. And I'm going to say that my cannon, oddly enough, actually, I didn't want it quite that steep of an angle. My cannon is going to shoot like that. So it does start exactly at this spot. But what I'm going to say is the velocity is going to be, I want to use the same numbers I used before so that I can recognize if I make a careless mistake. So let me check that out real quick. It's not that one, that's for sure. Yes, I am going to say this thing has a initial velocity of 20 meters per second. So this is going to be 20.0 meters per second. And it's going to be at 10.0 degrees downward. Okay. Now, you know what's going to happen is this thing is going to go like this and land right here. And that's going to be the range for this particular one. What I want to know is what's the range, what's the hang time, and what's the final velocity in vector form. Okay. So the first thing I'm going to do is draw, well, first thing I'm going to do is start writing out variables so that I can fill them in appropriately. So for instance, can anybody tell me, based on this coordinate system I've drawn, what is x0? That's the x position at time t equals 0. Anybody?
Repeat the question one more time.
What is x0, the initial x coordinate of the projectile?
Oh, is it just 0?
Yes, 0. How about y0?
80?
There you
80
go.
meters.
That's good. We'll deal with the velocities in a bit, but what about the acceleration? As a vector, do y'all agree that it's going to be negative g j hat? Okay. Now, I'm going to also consider this velocity by imagining it like this, say. Imagining this is 10.0 degrees. This is V0y. And this is V0x. And the sine of 10.0 degrees is equal to V0y over 20.0 meters per second. Everybody agree with that? Sine of 10 degrees is equal to V0y over 20 meters per second. And how about this one? cosine of 10.0 degrees is equal to V0x over 20.0 meters per second. So V0x is going to be, I think that was 19.7. So 20 times cosine 10 is 19.696. Now it's 3 sig figs, so technically I'd call that 19.7. But I carry extra digits when I'm doing intermediate calculations, so that's always, whoa, Nelly. So that's always good to help. So that's V0x. V0y is going to be 20 times the sine of 10 degrees. And that one gives me 3.47. And that's negative, of course, 3.4730. So I'm carrying 2 extra sig figs there as well. Okay, so you see, no matter what, the projectile, when you're solving a projectile problem, you're going to have to at least assume the initial velocity is something and then break it down into x and y components. Okay, so we've done that part already. Now I just need to write y of t and x of t. So y of t, again, we're going to use the 1/2 at squared. So this is going to be negative 4.90 meters per second every second times t squared minus, because this time the velocity is in the downward direction, so it's actually a negative. This is going to be minus 3.4730 meters per second. Again, those two are extra sig figs times t. And then the initial height is plus 80. So that's my y as a function of t. Does that make sense to everyone? Maybe y'all should try to write x of t and see if y'all get the same thing I do. Okay, so that should be x of t. Does that make sense to everybody? All right, so let's start off by let's find t hang time. I know that at t hang time, y of t has to equal 0. Therefore, what I'm going to say is 0 is equal to, now I'm going to drop all the units. I've written the units out so I know what things are supposed to be, and I need to keep track of that, but I don't need to show them now. I'm going to say negative 4.90 t squared minus 3.4730 t plus 80, like that. Now, in this case, there isn't a greatest common factor we can do. And in fact, to solve for t, we need to use the Pythagorean, or excuse me, the quadratic formula. So remember, the quadratic formula says if you have ax squared plus bx plus c is equal to 0, then x is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all that over 2a. If you complete the square on that ax squared plus bx plus c equals 0 one time, you'll probably never have to look that thing up again. But that being said, it is in the front cover of your book, so it's in your tests as well. So I'm going to use that. I'm going to say T hang time is equal to, now my negative B, notice B is actually already negative, so this is going to become 3.4730 plus or minus the square root of negative 3.4730 squared minus 4 times negative 4.90 times C for a C, which is 80.0. Notice the 80 had units of meters. The 4.90 had units of meters per second per second. So when you multiply those two, you get meters squared per second squared. Also, the 3.4730 had units of meters per second. When you square that, you get meters squared per second squared. So those two units can add. That's nice. Not only that, when you take the square root of them, you get meters per second, which is also the same unit that's in the numerator. All of that's going to be divided by 2 times A. And of course, the A is 4.90 times negative 1. So this is going to be negative 9.80. So we know the top has units of meters per second. We know the bottom has units of meters per second, or meters per second squared. So ultimately, when you divide meters per second by meters per second, you get just plain seconds. So all the units are working out. Things are nice. Any questions on that? Now I'm going to go through and be really conscientious about the units here and the sig figs, just so you'll know how I do it. So this is 3.4730. Those two guys are not sig figs. It's going to be plus or minus the square root. 3.4730 squared is going to give me 12.0617. Now remember that's 3 sig figs. So when I square it, you only have 3 sig figs. That means that's good up to 1 decimal place. And then the two negatives combine to give me a positive. So I'm going to do 4 times 4.9 times 80. And that number gives me 1,568 exactly. That also has 3 sig figs, which means in this case, it's only good to the tens place. So when I add these two numbers, I only have up to the tens place. That's something important because adding and subtracting is where the wheels fall off on the sig fig stuff. All this is going to be divided by negative 9.8. So if I take that 1568 and add to it 12.061729, that gives me 3.4730 plus or minus the square root of 1,580.06. Now remember, this is the whole reason I broke that up, is we only have sig figs up to the tens place. So that means the ones place and all these other guys are not sig figs. So I got 3 sig figs under the square root. I've already worked out the unit details. That's fine. So I'm going to take the square root of 1580. And that gives me the 3.4730 I already had, plus or minus. The square root is 39.74 9999, bunch of nines basically. The main thing is because it was 3 sig figs, all these guys are extra. And then I'm dividing all that by negative 9.80. So if I take the 3.47 and I add it, in other words, I use the top symbol because it says plus or minus. If I add it, then I get a positive number that's around 40-ish something. And then I'm dividing it by negative 9.8. That's going to give me a negative number. So that doesn't make any sense. But if I subtract it, I'm going to get a negative number, and then I'm going to divide it by a negative number. So that does make sense. So this plus sign is not reasonable or physical. Okay, so I'm going to use the bottom sign, which is 3.4730 minus 39.7. I'm just going to call that 7.5 because it's 5 with a bunch of zeros after it. That gives me, oops. That gives me negative 36.277. In this case, that was to, both of them are to the 10th place, the first decimal place, in other words. So that's actually there. And then negative 9.80. So I'm going to divide that by negative 9.8. And that gives me 3.7017 seconds. Now that's 3 sig figs divided by 3 sig figs. So, oops. So basically this 1 and 7 are non-significant figures. So I finally have one answer. T hang time is equal to 3.70 seconds. So this does occasionally happen. You sometimes have to use the quadratic formula to solve for time or other things. So just be prepared that that's one of the things that we do in physics. In fact, the main thing we do in physics is we assume that not only did you master every math class that you had since kindergarten, but that you not only mastered them, but you have them completely in your memory and can pull them up at any time. Okay. And by the way, we're also going to assume that you are the bomb of a student, and therefore you had a high school algebra 1, high school algebra 2, trigonometry, and then you went through the pre-calculus sequence as well as the calculus sequence. Now, I told you I was a deadbeat loser, so I went through those, but I went through those after college, once I got to college, because I, didn't do well enough to get to college in the first case. So don't worry, you can do it. It's kind of scary, but I just want you to know what you're getting into. That's the nature of physics. We assume you know all that stuff. All right, so we got that. Now, can anybody remember how we find the range once we know the hang time?
It's V initial times hang time multiplied by cosine theta.
Exactly, because you need the x component of velocity. That's why you said v initial times the cosine theta, and then you multiply that by the time, and that's how far it's gone to the left, or to the right in this case. So that's exactly right. So now we're going to do part B. R is equal to x of t hang time. So R is equal to, we got x hang time is 19.696 meters per second times 3.7017. Notice how I'm carrying those extra digits. That's the way you're supposed to do it. Carry the extra digits until the end. So I'm going to take this and multiply it by 19.696. And that gives me 72.909 meters. Now notice that was 3 sig figs multiplied by 3 sig figs. So these two are not sig figs, but I can tell you that the range is in fact 72.9 meters. Okay. Can anybody remember how we might go about getting the final velocity? Or can anybody tell me anything to help us figure out what the final velocity is? Is there anything we already know about the final velocity?
Would we put it in the y of t, but the t is the t of halftime? So we take the y function and put it as t of halftime?
Close. What you're forgetting though is we're wanting the velocity. So if you took the derivative of y of t first, that would give you the velocity in the y direction. And then you could actually apply that at t hang time, and that would give you the y component of velocity at the end. But do you know anything? How about this one, Infinity? Do you know what the x component of the final velocity is? Sorry to put you on the spot. Don't feel bad if you don't know, but it's a whole different ballgame when you're trying to answer questions in real
Would
time.
it be 0? No.
Look up and see, do you see any velocities that it was initially? You see that's the initial velocity in the x direction was 19.696, and the initial velocity in the y direction was negative 3.4730,
Mm-hmm.
and that's meters per second. Are either of those relevant to figuring out the final velocity?
Oh, yes, because we can find the magnitude using the final using the Pythagorean theorem.
Exactly. And not only that, since we're ignoring air resistance, the x component of velocity doesn't change at all. So when I go about doing this, V final is equal to question mark. What I know is V final x is actually equal to V0 x, which is 19.696 meters per second with those two extra non-sig figs. Okay. But the V final y is equal to d by dt of y of t evaluated at t hang time. I think that's what you kept saying to Infinity. I think you were making the same mistake I kept making, which was calling HT halftime. It's
Yeah.
hang time. The halftime was when we did a symmetric thing where it went from the same height and landed at the same height halfway through that path. I called that halftime. So we already did compute that velocity, that derivative by computing the velocity. It's right here. That's Vy of t. So all I really have to do is plug in the 3.70 seconds for that. So what I'm going to do is say V0y is equal to negative 4.9. Ooh, actually, I think I wrote that the wrong place. Sorry about that, everybody. I'm going to take back a bunch of stuff. That'll be the easiest way. Okay, so that was not where I did it. Where was it that I did it? Oh, I didn't do it in this one yet. Okay, so we can do it. So if I take the derivative of y of t, I think you can see I get negative 9.8 t, because the derivative of some number times t squared is 2 times that number times t. So I get Vy of t is equal to negative 9.80 t, and then minus 3.4730, like that. So now I can say V0y, or excuse me, now I can say V final y is equal to negative 9.80. I'll put the units in, meters per second every second, times 3.70. I think I had 17 was the extra digits. Yes. Seconds. Ooh. I don't know what happened just there. That was terrible. In seconds. And then I also had the negative 3.4730 meters per second. And that gives me V final sub Y is equal to negative 9.8 times 3.7017 minus 3.4730. That gives me negatives 39.7 0 like that. These are extra non-sig figs, and that's meter per second. And notice it's negative, which means it's downward. Okay, so now I've got the component of velocity in the vertical direction. I'm going to go ahead and draw a coordinate system really quickly. Now this X has a component of velocity that's unchanged. It's supposed to be 19.696 meters per second. And then the Y component is negative 39.75. So that's even bigger. So negative 39.7500 meters per second. And these two are at right angles. So that's how we use our Pythagorean theorem. This is V final. And this is phi. V final is equal to the positive square root of 19.696 meters per second squared plus negative 39.7500 meters per second squared square root. So when I do 19.696 squared, that gives me 387.93. So that's only a good digit up to the ones place. When I do 39.75 squared, that gives me 1580, but that's only to the tens place. So in fact, I have to round the sum to the tens place to get the right number of sig figs. So I'm going to say 1580 plus 387.932416. So I now get that this is the positive square root of 1967.995 meters squared per second squared. So now I took care of the sig figs issue. I'm going to take the square root of that. And that gives me 44.36, which, by the way, it only has 3 sig figs. So that's got to be 44.3. And then the 6.2 are not sig figs. So that's the magnitude. I'll also say the angle is the inverse tangent of, again, I'm not using the signs, divided by like this. So I'll take the inverse tangent of 39.75 divided by 19.696, close parentheses, gives me 63.64. Two. Okay, that was 3 sig figs and 3 sig figs. So really, I only get to count that. So finally, I can write that the final velocity is in fact 44.4
44.4 meters per second at negative 63.6 degrees. And that's it. We've done another projectile motion problem. Any questions on that? Oh, I ran over by 4 minutes. Sorry about that. You guys, of course, are free to go. I will wait here for the last person to leave. Feel free to ask me any questions you have. Good luck on your exam tomorrow. I gotta go change the date before I forget.
Thank you. Have a good night.
You too. Thank you, Jacob.
Thank you.
Thank you, Anna. And that's it, I guess. Anybody else in here? Nope, that's it. Bye, everybody.